Hello, hello. Now, welcome. Now we discuss about multiple choice question 2022 paper CC-7 semester 3 CBCS University of Calcutta B.Sc honors in mathematics. The question paper 2022 paper CC-7 question 1A. The differential equation of the system of circles touching the x-axis at origin is what? Now, since the circle touches the x-axis at the origin, this is the circle, this is the x-axis, this is the y-axis, origin. The equation of the circle x minus 0 plus y minus a whole square, x minus 0 whole square plus y minus a whole square equal to a square, where a is a parameter, center 0a and radius is a. From the equation 1, x square plus y square plus a square minus twice a y equal to a square. So x square plus y square minus 2ay equal to 0, equation 2. Differentiating 2 with respect to x, we get 2x plus 2y dy dx minus 2a dy dx equal to 0. Hence, x plus y dash minus a y dash equal to 0, where y dash equal to dy dx. Then a equal to x plus y dash by y dash. Substituting this value of a in equation 2, we get x square plus y square minus 2 bracket x plus y dash divided by y dash bracket close into y equal to 0. After simplification, we get x square minus y square within bracket into y dash minus 2xy equal to 0. This is the required differential equation. Hence, the correct option is 1. Correct option is 1. Next question 1b. Which of the following differential equations is not exact? For the given for the differential equation y dx minus x dy equal to 0, comparing with m dx plus n dy equal to 0, m equal to y, n equal to minus x. Then del m del y equal to 1, del n del x equal to minus 1. And hence del m del y not equal to del n del x. Hence y dx minus x dy equal to 0 is not an exact differential equation. Other differential equations 1, 2 and 3 are all exact differential equations. Hence correct option is 4. Question 1c. The general solution of the differential equation sin px cos y equal to cos px sin y plus p, where p equal to dy dx is what? Here, the given differential equation sin px cos y equal to cos px sin y plus p. So, sin px minus y equal to p, then px minus y equal to sin inverse p, or y equal to px minus sin inverse p. Obviously, this is a Clairaut's equation, Clairaut's form, y equal to px plus p. Differentiating 2 with respect to x, this p equal to p plus x dp dx minus 1 by root over 1 minus p square dp dx, or dp dx into bracket x minus 1 by root over 1 minus p square bracket close equal to 0. Hence, either dp dx equal to 0 or x minus 1 by root over 1 minus p square equal to 0. When dp dx equal to 0, we get after integration p equal to constant c. So the general solution of 1 y equal to cx minus sine inverse c. Actually this Clairaut form, so we can put for c in place of p for general solution of this Clairaut equation. Now extra part, this x from the factor x minus 1 by root over 1 minus p square equal to 0. We get p square equal to x square minus 1 by x square, or p equal to root over of x square minus 1 by x. Using this value of p in equation 2, then we get the element of p, this y equal to this, and this is a singular solution of the given differential equation. So correct answer is 2. Next question 1D, which of the following statements are false? Sin x and cos x are linearly independent solutions of d2y dx square plus y equal to 0 on minus infinity to plus infinity. E to the power x and x e to the power x are linearly independent solutions of d2y dx square minus twice dy dx plus y equal to 0 on minus infinity to plus infinity. E to the power x and e to the power minus x are linearly independent solutions of d2y dx square minus y equal to 0 on minus infinity to plus infinity. Sin x and 2 sin x are linearly independent solutions of d2y dx square plus y equal to 0 on minus infinity to plus infinity. Here, this option 4, sin x and 2 sin x. So, if this solution y1 and this solution is y2, then this y1 double dash plus y1 equal to 0, and also y2 double dash plus y2 equal to 0. This is the given differential equation y1 y double dash plus y equal to 0. So obviously y1 and y2 are two solutions of the given differential equation on this minus infinity to plus infinity. But y1, y2 are not linearly independent, because here Wronskian of these y1, y2 functions. So we get the determinant y1, y2, y1 dash, y2 double dash. We get sin x, 2 sin x, cos x, 2 cos x. So this equal to 0. So correct option is 4. Sin x and 2 sin x are linearly independent solutions, and this is the false statement for this. So correct option is 4. Note that this theorem, very important theorem for the Wronskian, if y1x and y2x be two differentiable functions on the closed interval AB, 1, if Wronskian of y1, y2 not equal to 0 for some x in the closed interval AB, then y1 and y2 are linearly independent on the closed interval AB. So, non-vanishing of Wronskian is sufficient condition for the linear independence of y1, y2. And 2, if y1 and y2 are linearly dependent, then the Wronskian is 0 for all x in the closed interval AB. That is, identical vanishing is a necessary condition for the linear dependence of y1 and y2. Here, P implies Q. If P is a mathematical statement and Q is another mathematical statement, then if P implies Q, then we say P is a sufficient condition for holding Q, and Q is a necessary condition for holding P. Contrapositively, negation of Q implies the negation of P. So this is the negation of Q equal to negation of P. Now, in the first note, this one, the sufficient condition, because Wronskian not equal to 0, this implies linear independent of y1, y2. Non-vanishing of Wronskian, W non-Wronskian not equal to 0, then y1, y2 are linear independent. So this Wronskian is sufficient condition for linear independence of y1, y2. And That is, contrapositively, not linear independence, that is the linear dependence, implies the Wronskian equal to 0. So obviously, Wronskian identical equal to 0 is the necessary condition for linear dependence of the y1 y2. So this is the identical vanishing is the necessary condition for the linear dependence of y1 and y2. So summarize this result, and we can extend Wronskian for in number of functions for this. So this is the important theorem for Wronskian here for two functions, Wronskian for two functions, one y1 and y2. Question 1 is the particular integral of d2y dx square plus 2 dy dx plus y equal to e to the power 2x plus e to the power x is what? Here yp equal to 1 by d square plus twice d plus 1 e to the power twice x plus e to the power x. So 1 by 2 square plus 2 into 2 plus 1 e to the power 2x plus e to the power x 1 square plus 2 into 1 plus 1, because 1 by fd e to the power mx equal to e to the power mx by fm if fm not equal to 0. Hence the result is this 4 e to the power 2x plus 9 e to the power x whole divided by 36. Correct option is 3. Question 1a. Which of the following is correct for the linear differential equation bracket 3x plus 1 bracket close into x d2y dx square minus bracket x plus 1 bracket close dy dx plus 3y equal to 0? Option 1, 0 is an irregular singular point. Option 2, minus 1 is an irregular singular point. Option 3, minus 1 is a regular singular point. Option 4, no irregular singular point. Here, the given differential equation can be written as this y double dash minus x plus 1 whole divided by bracket 3x plus 1 bracket close into x y dash plus 3 by bracket 3x plus 1 bracket close x into y equal to 0. Obviously, P1 is a function of x, this is equal to minus x plus 1 whole divided by this 3x plus 1 into x, and P2x is a function, this function 3 by whole divided by 3x plus 1 into x. 3x plus 1 into x. So this into x. Now x bracket 3x plus 1 equal to 0 gives either x equal to 0 or x equal to minus 1 by 3. So these are two singular points of the differential equation 1. Now x minus 0 into p, so obviously this minus x plus 1 by 3x plus 1, and x minus 0 whole square into p2, this equals to 3x square x plus 3 by 3x plus 1. So 3, this is the x square, so this is the only x, 3x by 3x square, so this is the 3x by 3x plus 1. Both are analytic at x equal to 0. Hence x equal to 0 is a regular singular point, because this x minus 0 into p1 is this function is analytic, and x minus 0 whole square into p2, this is equal to 3x by 3x plus 1. So both are analytic here. Next, for the point x equal to minus 3, x minus 1 by 3 p1, that is x 3x plus 1 whole divided by 3. So cancel this term, 3x plus 1. So we get x plus 1 by 3x, and x minus 1 by 3 whole square. So we get 3x minus 3x 1 by 3 square. Oh, sorry, x plus 1 by 3, 3x plus 1 by 3 whole square. So cancel this term. So we get 3x plus 1 3x plus 1 divided by 3 is 3 square. So both are analytic at x equal to minus 1 by 3 because in the denominator there is no term 3x plus 1. So x equal to minus 1 by 3 is also a regular singular point. Hence there is no irregular singular point. So correct option is 4. Question G. The domain of definition of the function fxy cos bracket 3x plus 4y minus log to the base e bracket 1 minus x square minus y square is what? Here log 1 bracket 1 minus x square minus y square to the base e. The domain is the D. This is the R2. All those points xy belongs to R2 space Cartesian plane. This such that 0 less than x square plus y square less than 1. So this is the circular disk. This is the interior point of this circular disk except the center origin. As for this log function, this 1 minus x square plus y square greater than 0. So obviously x square plus y square is less than 1. Obviously, because this log function is defined when this 1 minus x square plus minus y square is greater than 0. So obviously from this we get this. Also, logarithm is not defined at this point 0. So, uh, 0 greater than x square plus y square is less than 1. The domain of the cosine function cos 3x plus 4y is R2. Actually, when x square plus y square equal to 0, log 1 is 0. And this is also actually question answer is logarithm is not defined at 0. Logarithm is not defined at when x square plus y square equal to 0. Then this part is 0. So log 1 to the base e is 0. So domain of the cosine function is the R2. Hence the required interval is actually correct answer is this. Logarithm is not defined at 0, but here if we put x square plus y square equal to 0, then log 1, and the log 1 is 0. So this is the correct answer is x square plus y square may be equal to 0. If we put 0, log 1 is 0. So correct domain answer is this. Correct answer is this. So correct option is D, not 3. If we put x square plus y square equal to 0, then x square plus y square equal to 0, then this is the log 1. So log 1 is 0, and this xy 0, cos 0 is 1. 1 minus 1, log 1 0. So this is the value of fx is cos 0. Cos 0 is 1. Correct answer is 4. Question H. Correct answer is 4. value of the limit, double limit xy tends to 0, 0, x sine bracket x square plus y square divided by x square plus y square. Here we put polar coordinates x equal to r cos theta, y equal to r sine theta, x square plus y square equal to r square, when r tending to 0, as xy tending to 0, 0. So modulus of fxy equal to modulus of x sine x square plus y square whole divided by x square plus y square. Hence, this x equal to r cos theta and sine r square divided by r square. So this equals to mod of r, mod of cos theta, mod of sine r square is the r square is positive, so this is r square. This is less than equal to mod of r, mod of cos theta is less than 1, less than equal to 1, so this is less than equal to 1, and mod of sine r square is less than equal to r square whole divided by r square. Since r square not equal to 0, so we cancel r square, so this is equal to mod of r. This less than epsilon, say epsilon is a very small positive quantity. If r square is less than epsilon square, or if 0 less than x square plus y square less than delta square, this is equal to epsilon square. Thus, mod of fxy minus 0 is less than epsilon whenever 0 less than x square plus y square less than delta square for any epsilon greater than 0. Hence, limit xy tends to 0, 0 if xy equal to 0. Correct option is 2. Question I, for the function fxy equal to x square minus y cube minus x square y plus y, the point 0, 1 by root 3 is not critical point, is a saddle point, is a point of local minimum, is a point of local maximum. Now, del f del x equal to this, del f del y equal to this. For extremum value, del f del x equal to 0 equal to del f del y. Hence, we get 2x bracket 1 minus y equal to 0 and 1 minus x square minus 3y square equal to 0. And this from this, either x equal to 0 or y equal to 1. When x equal to 0, from the second equation, 1 minus x square minus 3y square, we get y equal to plus minus 1 by root 3. And if y equal to 1, from the first equation, from the second equation, we get x square equal to plus minus root 2y, which is impossible. So stationary points are either 0, 1 by root 3, 0, minus 1 by root 3. And in this case, y equal to 1, x are imaginary, so it is not accepted here. Now, del 2 f del x square equal to 2 minus 2y, and del 2 f del y square equal to minus 6y, and del 2 f del x del y equal to minus 2x. Now, if xx 0, 1 by root 3 is equal to positive, and if a capital H is equal to fxx into fyy minus fxy square, this is equal to this, and minus 12y bracket 1 minus y minus 4x square. Capital H at the point 0, 1 by root 3, this is negative. Fxy has a saddle point at AB if capital H less than 0. So here, obviously, 0, 1 by root 3 is a saddle point. In this example here, 0, 1 by root 3 is a saddle point. Correct option is 2. Question J, the unit normal to the surface x square plus y square equal to z at the point 1, 2, 5 is what? Let phi is the surface x square plus y square minus z. Del phi del x equal to 2x, del phi del y equal to 2y, del phi del z equal to minus 1. So gradient of phi is equal to del phi del x I cap plus del phi del y j cap plus del phi del z k cap. Hence we get 2x I cap plus 2y j cap minus k cap at the point 1 to 5. Here the given point is at 1 to 5. At the point 1 to 5, gradient of phi is equal to 2 I cap plus 4 j cap minus k cap. So modulus of gradient of phi is equal to root over of 21. Hence, the unit normal vector at the point 1 to 5, this n cap equal to gradient of phi by mod of gradient of phi. Hence, this is the answer is 1 by root 21 2 I cap plus 4 j cap minus k cap. Correct option is 4. Thank you for watching this video.